Hey guys, just checking in here on Chapter 19, Section 3 on combining electric forces. On Sections 1 and 2, if you refer to my Weebly, I have Khan Academy videos that are pretty good explaining those. So take a look at those if you are having troubles on Sections 1 and 2. So Section 3 are combining electric forces. Basically, what happens to the electric force when multiple charges are involved? All right, so we look first at Coulomb's law for the strength or the magnitude of that force between charges. And what this shows us, okay, and what Coulomb's law is that the force between these charges depends on the constant K, which is 8.99 times 10 to the ninth, times the magnitude of each of the individual charges, that's these guys, Q1 and Q2, divided by how far apart they are squared. So don't forget that square when you're doing these types of problems. And that will give you the force between these, either an attractive force if the charges are opposite. Remember, opposite charges, positive and negative, will attract each other. Like forces, like two negatives or two positives, will repel and push apart. So moving on, here we see examples of different charges. So we see the effect on charge 1. So we're looking at what is the effect on this charge from the two separate charges. And it gives us our forces. Now the way this reads, that F sub 12 is the force on charge 1 from charge 2. So because these are both positive and they repel, that charge goes in this direction. It's the force on 1 from 2. Now, the force on charge 1 from 3, again, they're like charges, so they repel. Force on charge 1 from charge 3. Now, getting these two vectors, if we do our vector addition, okay, and here's our 1 on charge 1 from 3 and on charge 1 from 2 gives us this resultant vector. So once we get our components, we could add them together and get the total force. Now, what we're going to do is more one-dimensional, left and right, instead of two-dimensional like these. And I'll go through the example that is shown on your homework and give you a good setup for that. All right, so moving forward, this vector addition gives us our total force. Now this could be two charges, 3 charges, as many as you want. So here, and this is one more similar to what you're going to see in your homework. So it gives us a charge, okay, charge 1, and it's at the origin. Okay, so this charge 1 at the origin, right here, gives us a charge of negative 5.4 nanocoulombs. So that's negative 5.4 times 10 to the negative 6 coulombs. Remember, coulomb is our unit of charge. Now, be careful, it shows charge 3 next, then charge 2. And it tells us how far apart they are. Notice they're in meters. On your homework, what's given to you is centimeters. So you have to convert those to meters. Okay, on question 3, 4, and 5 in your homework. 12 centimeters and 15 centimeters. So that's 0.12 meters and 0.15 meters are the numbers that you need to use. All right. So if we, in this problem, want to find out the total charge on 3, okay, that's what it's asking us here in this problem. Well, charge 1, because it's an opposite, charge 3 is positive, 1 is negative, it's going to pull it to the left. Now the left is a negative value. Remember in physics, negative is a direction. And charge 2 is also an opposite charge, negative, where 3 is positive, so it's going to pull it to the right, making that positive. So we are going to use our numbers, okay, our two charges. We're going to have to do charge 1 and 3 to figure out the force of 1 pulling 3 to the left. Then we're going to have to do charges 2 and 3, finding the force of 2 pulling 3 to the right. So the next slide here shows that. Okay, so the force of 3 on 1. Now notice, because it pulled it left, look at what they did here. They put the negative in the value. They just put it in there to show the direction, okay, and it gives us that in the answer. So if we start plugging in our values, negative 8.99 times 10 to the 9th times the value of our 2 charges, okay, and that's what this line gives us, over how far apart they are squared. And the force pulling it to the left is negative 0.14 newtons. Okay, then we do the force on 3 from 2, from the charge that was to the right of the one in the middle. Again, plug in our values, okay, and that's what they did here. 0.25 meters apart is how far those 2 were apart. And we get this 0.51 newtons. Now, from there, because these two are our combined forces, we add them together and we get a total of 0.37 newtons. So what that means is these two forces pulling on charge 3, that charge in the middle, that charge in the middle is going to move to the right, okay, because there's a net force of 0.37 newtons pulling on it to the right. Before I move on here, let's set up what we have. Alright, so on our problem that we have in our homework, we have 3 charges. Okay, so we're going to have charge 1. Okay, it says charge 1, positive 9.9 nanocoulombs plus 9.9 times 10 to the negative 6 coulombs. And that's at our origin, x equals 0. Okay, then it says charge 2 is at 12 centimeters, 0.12 meters. Okay, and that charge is negative 5.1 times 10 to the negative 6th. And then charge 3 is at 15 centimeters, okay, or 0.15 meters, and that charge is 4.4 times 10 to the negative 6 coulombs. So here are our 3 charges. So what question 3 asks is the charge on 3. Okay, so we got to figure out this one. Well, if we look at 1 and 3, okay, the force of charge 1 on charge 3, we have 2 positives, so it's going to move it to the right. It's going to push it away. So if we look at the force of charge 1 on charge 3 is going to move it to the right. It's going to be positive. And then if we look at the force of charge 2 on charge 3, okay, they're opposites. It's going to pull it together. It's going to make it go this way. All right. So you might be looking at this saying, oh man, I got to do that equation 6 times. No, you don't. Because forces are equal and opposite, the force of 1 on 3 is the same as 3 on 1. So here's what I mean. Questions 4 and 5 are going to ask about charge 2 and charge 1. So if I look at charge 2, the force of charge 2 by 3, okay, negative and positive, it's going to move it to the right. Okay, it's going to be positive. Now these values are the same. So whatever you got here is the same value there. Okay, and then when you do the force of charge 1 on charge 2 is going to pull it to the left. Opposite charges attract, so that value will be negative. Now we haven't figured that one out yet, but we will. All right, and then the last question asks about charge 1. So we got to look at the force on charge 1 from 3. These values are the same. And then if we look at the force of charge 1 from charge 2, these values are the same. Okay, so once you get those values, just reuse them. Okay, and add them together and you'll get your total forces on each individual charge for questions 3, 4, and 5. So moving forward, this just starts going into 2 and 3 dimensional vectors. We're going to be doing straight line vectors, but you would do them the same way. We did this earlier in the year where we did vector addition, and you can find magnitude and direction of these vectors. Alright, so now what we're going to talk about is start talking about spheres. Okay, and one of the interesting things about spheres is as it's charged, the center of the sphere has no force on it because it's essentially canceled out by a force on the opposite side. And in the middle of a sphere, you get no total. Alright, so this is going to start getting into density, which we're not going to do a bunch of, but essentially density of a charge gets bigger at a point. That's why lightning rods come to a point to attract that. Alright, skip by this, and we don't need to do that.